Hello everyone, my name is Amin Nikanjam, a research associate at Polytechnique Montreal, and now I am going to present you an empirical study of design smells in deep learning programs, which has been conducted by me and Professor Futscom at Polytechnique Montreal. Nowadays, we are witnessing a growth of deep learning application in various domains, from personal banking up to autonomous driving. The total market was about $2.28 billion in 2017, but it is expected to be more than $18 million by 2023. Moreover, about 76% of enterprises now are prioritizing artificial intelligence and machine learning in their IT budgets. To apply deep learning in a particular domain, a deep learning program is developed. It consists of deep model, training algorithm, and data. During the development, the researcher or developer has multiple design choices. For example, selecting type, size, number, and order of layers to construct a particular architecture, or select optimizer function, regularization, and activations to configure the model. All those design choices, indeed, may affect the quality of the deep learning program. For example, one may see a poor performance after deployment of such program. By poor performance, we are saying about low prediction accuracy, which is expected to be high in such programs. Well, according to the importance of quality of deployed DL-based software system, in this paper, we are studying design smells in such programs. Actually, design smells are defined to be poorly designed or configured models, which may degrade the entire performance of the system by showing low prediction accuracy. In ML-based system, the accuracy can be regarded as a functional requirement since the prediction accuracy of the system is expected to be high. Moreover, in this paper, we are targeting design smells in a particular deep architecture, which is called deep feedforward neural network. This architecture has been used widely for different applications and is popular in deep learning community. Deep feedforward neural network is principal architecture for solving classification and function approximation problems. By feedforward, we are saying about forward flow of information from the input layer to the output layer, which passes through hidden layers as well. Various kind of layers can be used in FNNs. For example, dense layers, which are fully connected consecutive ones, or convolutional neural networks, which consist of convolution and pooling layers. This architecture is very popular for image-like data and videos. Moreover, the developer can use regularization functions to improve the performance of the network and avoid local optima during training, for example, dropout and batch normalization. Let's consider an example of design smells from one Stack Overflow post. The developer complains about the low prediction accuracy in this model. In our study, we have identified the problem as non-expanding feature map. Actually, the developer failed to extend the feature map as model gets deeper. In the consecutive convolutional layer, you are seeing that the developer failed to expand the feature map. So the extracted features are irrelevant and the model is expected to show low prediction accuracy. Now we briefly review our methodology. There are two main resources for deep learning programs with design issues or bad performance. Stack Overflow, where users mention their questions, and public datasets that have been published by previous researchers. After reviewing these resources, we ended up with 659 deep learning programs with bad performance or design issues. Moreover, there are some research papers that discuss best practice or bad practices in designing deep learning models. After reviewing all these resources, we ended up with 8 design smells in deep learning programs. To assess the relevance of these design smells, we run an online survey with 81 deep learning practitioners and developers. Finally, we analyze our findings. Now I briefly review the identified design smells. First, let's consider the typical structure of convolutional neural network. First, convolution and pooling layers extract features from the input image. finally, dense layers perform the classification task based on extracted features. The first design smell is non-expanding feature map, which is about keeping the number of features the same as the architecture gets deeper. Consequently, the network will lose some promising features, leading to low accuracy. The second design smell is losing local correlation, which is about growing the window size of convolution when the model gets deeper. Otherwise, the model will fail to extract useful features. Smell number 3 is heterogeneous blocks of CNN. Actually, having only one convolutional layer with proper configuration at each stage is not a good practice. It is advised to have a block of 2, 3, or even 4 homogeneous convolution layers with similar characteristics at each stage. Smell number 4 is too much downsampling. Again, having one pooling layer after each convolution layer is not a good practice. Actually, it is advised to keep the number of pooling layers as about 1/3 of the number of convolution layers. So after about 3 or 4 convolution layers, it is advised to have a pooling layer to not losing useful information extracted in early layers. Smell number 5 is non-dominating downsampling. It is advised to use maximum pooling instead of average pooling, especially for image-like data. This may help to capturing invariances in data, which is very important in image-like data classification. The smell number 6 is useless dropout. Using dropout before downsampling layers will counteract its effect. The best practice is using dropout layer after maximum pooling. Otherwise, neutralized dropout after pooling may lead to overfitting. Smell number 7 is about using batch normalization with bias. Batch normalization as a regularization technique will be mostly effective if it is used without bias. Smell number 8 is about calculating non-representative statistics. If we put batch normalization after dropout, this may lead to computing non-representative global statistics of data. So the best practice is having the dropout as the last layer in such structures. We have conducted an online survey with 81 deep learning developer or researcher to assess the relevance of the identified design smells. Among participants, the majority of them have between 1 and 3 years of experience in research or development of deep learning applications. 20 have less than 1 year, 10 between 3 and 5, and 10 more than 5. Python is the most popular language in our survey. Among deep learning framework, TensorFlow with 59 votes is the most popular one. Based on the result, we can say that participants acknowledge the relevance of all smells. To have some detail, non-representative static estimation received the maximum positive vote by 68%, and heterogeneous blocks of CNN received the minimum negative vote by only 10%. On the other hand, losing local correlation received the minimum positive rate among all smells. At the end of our survey, we have a quick question about usefulness of a detection tool. Almost all of the participants, about 90%, acknowledge that having a tool for detecting such smells can be useful and they may use it. Among comments we have received in our survey, I would like to highlight 2 of them. Considering the whole pipeline of machine learning from data gathering up to deployment, some participants stated that hyperparameter tuning is inevitable after any initial design to improve the performance, even when avoiding design smells. Moreover, the choice of design and configuration depend on data, preprocessing, and domain. So, some experiment is necessary in each domain and problem to find the proper design and configuration choices. To be concluded, we have identified 8 design smells for convolutional deep feedforward neural networks. The smells have been validated by 81 deep learning developers in an online survey. Although avoiding identified smells will save time, effort, and computational resources during design and test, some experiments, especially for hyperparameter tuning, is inevitable. Thank you so much for your attention, and please let us know your comments and questions. Thank you again.